And you have a companion star that's 18 solar masses, and it's been determined that the black hole mass here is about 10 solar masses. So it's so high, we know for sure there's no way this can be a neutron star. So that was confirmed to be the first stellar black hole. Now, the ones that I'm really interested in are the ones that are really, really massive. Bigger is better. And this was done just not that long ago, but it was done with the Hubble Space Telescope. And the reason is that we need to actually go very, very close to the center. And I don't know if you can see this little blue box here. And that's exactly sort of the same area as you see here, this blue box. And we took that light and sort of put it through a prism. You've probably seen light scattered through a prism, see these beautiful like rainbow colors, right? So that just splits the energy of the light into different colors. And that's how they kind of color-coded it here. But what it really is, what this is showing is that this is the spatial axis. So that means this is going across the galaxy like this. And then what we're seeing here is the gas that has high velocity from the systemic velocity. What we see sort of deviate from the central part here. Okay? And what this shows is that as we go closer and closer to the center, some of the gas is moving at really high velocities. And it's color-coded such that this actually means that this gas is moving away from us. It's redshifted. And really, really close to the same part of the core here, then all of a sudden, this gas is moving away from us at a very high speed. And then as you go further away, it kind of tapers off in the velocity. And that shows that there's something in a disk. It's moving really fast. This gas is moving really, really fast. And based on the velocities here and the distance from the center, we can determine the black hole mass, or the central mass. And that was the first determination that we have something really, really compact in this particular galaxy. But the one that you probably know the most of is this particular galaxy that is our own galaxy. And it's actually the best detection of a black hole that we have. And it's supposed to actually have a little movie. There we go. Okay. So what this is showing is that we actually managed to peer all the way into the very center of our galaxy using the techniques, some special techniques that's actually let us see the light from the nucleus, and been able to trace, just by taking images at different times, been able to trace the position of the stars. This is actually the first time that we're seeing something actually move in outer space. Because quite often things move fast, but they have such large distances to move that we don't see them actually move on the sky. So this is one of the first ones for this. But it also shows, just by actually measuring these orbits, Keplerian orbits, that means that they're moving on an ellipsis, just chuckling along, but they're moving really fast because this particular star, which is the one that's called S2, can actually do a full orbit in like 15 years. And based on these orbits, we've been able to determine the black hole mass, which is about 4 million solar masses. Okay? I have another animation here that actually shows a little better it actually shows you in the end how wide this the orbit is. So the black hole is down here at the locus of all these different ellipses of the stars moving around. And as you can see, it's actually kind of fun to see it speed up just like a comet. Speed up right around the gravitating object. And this is 2 light days across. That means it takes light 2 days to cross that distance. So you can see this is very close. It's within light hours. So these stars come really close. You want to have a look at it again? Let's see if I can do that. Apparently this microphone doesn't like me.
You're too close to the loudspeaker.
Is that where it is? Okay. I'll move away.
Feedback.
Yes, yes. Thank you.
Don't feel bad, you didn't like the other guy 2 weeks ago as well.
I feel so much better.
Learning by doing.
What's that?
Learning by doing.
Yes, exactly. Learning by doing. So yes, I can actually sit, it's like watching the fire. I can sit and watch these stars orbit for hours because I just think it's so fascinating. So based on these orbits and these very fine, that just going over and over again, we have a very secure, the best ever measurements that this is a black hole in the center. Because we can go so close, we can tell that there's nothing else that we can imagine is causing this matter. The other thing is, maybe you need to see it again, because I should point out that the fact that this star, when it comes down here, doesn't wobble, tells us that it's not a star cluster. If it was many small objects that was making out a really large gravitating matter together, we would see that star wobble as it comes down around here, but it doesn't. It goes straight through, just smooth. That in itself tells us it's just a single object that we're looking at. Okay, I'm sure you're tired of looking at that movie. I know. Yeah, again. We can show it afterwards, okay? I have another movie I can show you where we fly through the galaxy. All right, so why are we even interested in these massive black holes? Now, we determined that they exist, but why do astronomers really care? I mean, is it just a curiosity? Is it just this, well, theoretically we know they should be there, and now we determine that they are? Well, really not. The reason is, if you look at the universe, this is actually a very, very deep image that was taken for Hubble Space Telescope. We're staring at the same little patch in the Ursa Major, so that's the Cosmology, for those of you who know what that is. Just above it, there's a very clear patch that looks dark. Looks as if there's nothing there. And astronomers actually decided to have a Hubble Space Telescope stare at that for 10 days and 10 nights, almost straight. We'll take lots of images such that we have the equivalent of a very long exposure that's equivalent of 10 nights. And we're really surprised to see that it's just filled with galaxies. And some of them, like spiral galaxies and elliptical galaxies, and some of them look like train wrecks. Right? It doesn't look very, you know, like normal galaxies as we know in spiral galaxies. But all of this except us are galaxies. All these little specks are galaxies. And now what we know is that probably all these galaxies contain supermassive black holes. Pretty cool, huh? Well, we think so, because it turns out that when we look at these black holes, there tends to be, this is showing the black hole mass. If we measure the black hole mass and then measure the mass of the galaxy, there's a really nice correlation that shows that galaxies that have a large sort of spheroidal component that we call bulge, those that have this large bulge have also a very large black hole. The ones that have a really small one have a really tiny black hole. So the Milky Way, oops, where did okay, I forgot to put the Milky Way on it, but it's supposed to be lying right there. I used to have one that showed that. Okay, so the Milky Way is right there. And right now, this is an old slide, because there was a point in time when we thought those galaxies that don't really have much of a bulge, they probably have no black hole. But we do know now that it's not actually true, because we know of a galaxy that has no bulge, but it's active. The black hole is active, and we can measure the mass of the black hole that way. So we know that all galaxies probably have black holes in them. And when we measure the black hole mass and compare it to that of the galaxy, it turns out that the mass of the black hole is about 1,000 of the galaxy. So there's this very nice correlation that the bigger the sort of spheroidal component, or the egg part of the component, the larger the black hole. And that probably tells us something about how these galaxies formed and evolved. Somehow, something as tiny in this, on the scale of the solar system, knows about what's going on in this huge galaxy, because some of these galaxies are so large that it takes more than 100 million years for light to cross it. So it's large, huge. And how on earth does this little black hole, I mean, it looks big here, right? That's how we draw it so you can see it. But this big black hole there, or this little black hole, big black hole, but with a small extent, I guess that's what I should really call it. How does that know about this big bulge out here? So we're thinking there must be some causal connection. That means maybe in the evolution, the two know about each other. They can talk. We just don't know how. But somehow in the evolution, they go hand in hand. Maybe because they were born the same way, and they had the genes in them that had to grow in sort of in sync. Or maybe it's, you know, the whole Hubble time of evolution that landed them on this relationship in the nearby universe, because we can only measure this for the nearby universe. But it tells us that there must be a connection between the formation and evolution of the two. Now, so the big question, another big question is, okay, so we have black holes in the centers of these galaxies. what possible role does these black holes actually play in the characteristics of these galaxies? We have galaxies that look like this, spiral galaxies like our own Milky Way. We have galaxies that are more irregular, that look more like train wrecks. But they have, what's actually common between the two is that they have lots of young stars. They have lots of gas and dust, but they're forming stars like crazy. They have lots of gas, so they're forming stars. And we know as soon as we have gas in a galaxy, it'll form stars. Then on the other hand, oh, I should say, they turn out to be blue as well. They look very blue because these very young blue stars outshine all the red little dim ones. And then when we look at elliptical galaxies like this one, they're kind of red, and they have really old stellar populations. They're not really forming stars at all. They really don't have any gas. So they're just sitting there like old grandpa looking at all the other ones and going, yeah, in my young times. But the thing is, how did they come to be? What's the connection here? All right, so the thing that we're thinking when we look at these stellar populations, we can tell that there's a very narrow range in the stellar populations of these elliptical galaxies. They're all very old. They don't have any young stars. Yet when we look at the stellar populations over here, we have old stars, we have young stars. So it shows that very suddenly the star formation must have turned off in these elliptical galaxies. Yes. So the big question is, what really stops star formation? Could the black hole actually help to do that? Because there's probably a black hole in the center. Another thing we're thinking, okay, we know in order to make elliptical galaxies, you can actually just slam two spirals together. And in what way might the black hole here actually have a role to play? And this is where I'm going to show you a movie, a little movie, short movie, okay? But to sort of lead up and actually tell you what's going on. So there's some researchers actually doing simulations. And they ran two types of simulations. They were actually slamming two galaxies together, which is what you can kind of see different time steps in their simulations. In the bottom part here, they have two galaxies that have no black holes in the center, but they have lots of gas. This is actually the gas phase you're seeing. You're seeing no stars, you're just seeing all the gas. And when they're interacting, all that gas comes into this very center, and it gets heated a little bit, but it actually gets a large concentration of gas in the very center. And one of the things that we do know is that there's gas, star formation will happen at some point when that gas cools enough to collapse and form stars. So that's a problem. We see something that's actually round, like an elliptical galaxy, but it's forming lots of stars. Okay? So it can't be our elliptical galaxies because they don't form stars. So the interesting thing is, if they actually put a black hole in each of these galaxies and slam them together, something happens. At some point when gas falls onto the black hole, they light up. Heats all the gas that's coming into the center and actually blows it away. Heats it and blows it away. And they can actually this way avoid that they have a stellar system that's round and spheroidal, like an elliptical galaxy, but it's not forming stars. So theorists are thinking this may be a way that we can form elliptical galaxies, and maybe the universe did exactly that. So let me just actually show you, oops.